So now we're going to wrap up our short unit on radioactivity discussing the concepts of half-life and fission and fusion. So our discussion of half-life here is going to be pretty minimal. We're going to do some activities in class that hopefully help make this a little bit more concrete. But the half-life of a radioisotope is just the amount of time that it takes for 1/2 of a sample to decay. So for example, iodine has a half-life of, iodine-131, has a half-life of 8 days. And so as it decays, or as time passes, it begins to decay. So after 8 days, if we had a 1 gram sample, after 8 days, we would have a 1/2 gram left. After 16 days, we'd have a 1/4 gram left. After 24 days, we would have 1/8 of a gram, and so on. And so one of the things you can see with half-life is that if we were to graph or plot the decay of a radioactive element, you could see that it decays exponentially. And so even after just a short number of half-lives, most of the material is gone. But if you remember from math, in an exponential decay curve, we never actually get to 0. So there's always going to be some chance that some of that material is still radioactive. And I'm not going to spend a lot of time discussing it in this video. We'll do an activity in class. We use half-life to be able to date ancient objects, and so the most common way to do that is carbon-14. And so we're going to do a little activity in class where we experiment with how a scientist would figure out how old something is based on how much carbon-14 is left in the sample. And scientists do this using the decay curves for carbon-14 that they know from their research for how long it takes carbon to decay. All right, so the next thing we're going to cover is nuclear fission. And nuclear fission is when a radioactive isotope is hit with, usually it happens because it's hit with a neutron, and that neutron causes the nucleus to become unstable and split spontaneously into two new elements, okay? And usually that process generates more neutrons, which could then cause the same process to happen with other nearby isotopes that are also susceptible to undergoing fission. So, and fission requires these same, or has the same rules about conserving mass number and charge as the reaction occurs. And so what you can see here is that when one neutron bombards the uranium-235 nucleus, it's now uranium-236 because we've added 1 to the mass number. And then when it splits, the mass numbers of each of the products has to add up to that 236 that we started with. Okay, so in this process, there is actually a teeny bit of mass that is released, and then that's converted to energy. That's where the energy comes from. And we know this from Einstein's theory of relativity, E = mc squared, where E is energy and m is the mass. But it's a teeny, teeny, tiny amount of mass, and we're not going to worry about it in terms of our mass number. What you need to make sure is true is that you have the same number of protons and neutrons before and after the fission occurs. So I alluded to the fact that when fission occurs, usually you get more neutrons, which then generate more fission reactions. And this is called a chain reaction. So in a chain reaction, there's a rapid increase in the number of high energy neutrons available that react with more uraniums. And so what happens is you would just have to input 1 neutron, and the result is that all of these uranium atoms that are present in your sample start to undergo fission because each of them becomes bombarded with another neutron, and then that reaction or that fission causes more neutrons to be released, which in turn causes more, and so on. So all of the atoms undergo this reaction. Okay, and then the final type of radiation we're going to talk about is fusion. And we don't yet really have a way for fusion to happen here on Earth, at least not in a way that's productive in terms of forming energy, or producing energy, sorry. But it happens all the time in the sun. And so fusion is when 2 small nuclei combine to form a larger nucleus. And just like I said before with the fission, a small amount of mass is lost, which we can't see in terms of a mass number, but that generates a tremendous amount of energy. And again, we have this same rule that applies, that the mass numbers on the left have to add up to the same thing as the mass numbers on the right, and the same thing with the protons. Okay, so this concludes our discussion of nuclear chemistry, and we'll continue to work with these and practice these in mastering chemistry.